Welcome. This is the presentation of my diploma thesis with the title Evaluating Sentinel-2 Super Resolution Algorithms for Automated Building Delineation for the submission to the AGEO Award 2026. The motivation behind this thesis was that the development of super resolution algorithms has developed dramatically over the last couple of years, and more models are being applied to Earth observation images such as from Sentinel-2. Super resolution increases the spatial resolution of images, and in the case of Sentinel-2, that's from 10 meters up to 2.5 meters, which subsequently allows the application of Sentinel-2 images for many more use cases. But the question remains how we can evaluate super resolved images, especially in the context of determining how trustworthy these super resolved images are. There are metrics available which do these tasks, but they lack one major point, which is that they do not evaluate the suitability of super resolution in real-world scenarios. Thus, no uniform evaluation framework is currently available, which works with such real-world use cases in Earth observation and with super resolution. And the goal of my thesis is to create such an evaluation framework on a specific task of building delineation focused on Austria. I framed a couple of research questions to outline this task, with a full set of them being available in the publication. The two questions I will focus on here are whether first, super resolution algorithms are actually advanced enough to be used in real-world applications, and secondly, whether certain super resolution algorithms might perform better than others and why. I separated the methodology into 3 individual tasks. First, the task of creating a high-quality dataset supporting such an analysis. This includes 3 different data sources. First, Sentinel-2 images, rasterized building masks, which are extracted from the Austrian cadastre, and finally, high-resolution aerial images. The download and the processing of all of these sources was combined in a specifically developed Python package, Austria Downloader. The next step was the gathering of super resolution models, in this case 7 models from 6 publications, and then the subsequent training of building delineation models, but not only on the super resolved images, but also on simple interpolation-based Sentinel-2 images. I included these interpolation datasets because I wanted to include them as a simple and efficient deterministic comparison baseline. Additionally, one dataset containing the high-resolution aerial images is included as well. It functions as a validation tool to determine if the whole processing pipeline works at a given resolution of 2.5 meters. Now, already heading over to the results. The first assessment shows that the building delineation works best if it's trained on high-resolution aerial images, which are resampled to 2.5 meters. This is as expected because these image sources contain the most high-resolution information and are guaranteed to have no hallucinations. Next, we can determine if super resolution algorithms are advanced enough to be used in real-world applications. And it turns out that that's not the case. In a conducted experiment, given the dataset and the models, interpolation methods still perform better than the best performing super resolution model. Not only that's the case, but they're also much less resource intensive than training high and complex super resolution models. To answer the second research question, whether certain super resolution models perform better than others, we can say that that's certainly the case, and that there are 2 major distinctions which can be made here. The first one being the training dataset, where using a complex synthetic dataset or using real high-resolution reference data works better than using synthetic data for training the super resolution model. Additionally, using non-generative super resolution model backbones works better than using generative ones. To conclude, new insights include that the interpolation methods still perform better than super resolution, and that there are differences attributed to using different super resolution models. This results mainly from using different training datasets and the super resolution model type. But this is only one use case of many possible use cases for super resolution on Sentinel-2, so it would be really interesting to expand this methodology and apply this evaluation framework to more different use cases, which might capture the whole image in full. Thanks a lot.